Good evening, dear students of class 12. We shall continue with the next topic of chapter number 2 of our curriculum. Now, today we shall first find out a formula for potential due to a point charge at a point. And we would also learn how to integrate, and finally in the last section of this video we shall draw a graph between potential and the distance between the charge and the point. Now here let us go back to the revision of what is the meaning of potential. As per our remembrance, the meaning of potential is bringing a unit positive charge from infinity to the required point P in the vicinity of a charge Q which has its own electric field. So we are trying to shift a unit charge from infinity to a point P in the vicinity of the charge Q. Now, before starting this derivation, let us first learn some amount of maths which is required to derive this formula. So, let me go to the next page, then I shall come back to this page and we shall do the derivation. Okay, so let me go to the next page here where I am going to talk about integration which is required for this derivation. Normally, teachers complete the integration in the standard 11th itself and the maths is followed. But I am a kind of teacher who would do the integration for that particular topic and for that particular year so that it is easier for you to actually apply the integration formulas. Now, yesterday in the video, I have already told what is the meaning of integration. Integration is nothing but summation of small parts. When you want to add up small parts, you have to do overall integration. For that, we have a formula. Okay, the formula for integration is, this is the symbol of integration, x raised to n dx. Okay, you can even write r raised to n dr. Okay, the variable is the same as you can see. Now, whether it is x raised to n dx, the answer of the integration is n plus 1, x raised to n plus 1 upon n plus 1. Here it is r raised to n plus 1 upon n plus 1. Now, some of you may not be quick enough to remember the formula n plus 1. You have to just create your own trick. Now, what is the creation of the own trick? We will do with one example. Example, r, if I simply write r, it is r raised to 1 dr. What is the power of r at present? 1. So 1 plus 1, power plus 1 upon power plus 1 is the answer. So what is my answer? R raised to 2 by 2. Okay. X raised to 2 dx. I am using two variables. Now what is the power here? 2. So what should I write here? The variable is x. Power plus 1. So 2 plus 1 upon power plus 1. So 2 plus 1. So what is my answer? X raised to 3 upon 3. So what I have to remember? Write the variable. Write the power plus 1 divided by power plus 1. That is the formula I have to follow for any integration of this kind. Suppose the power is negative. R raised to minus 1 dr. Power is negative. You can also write it as integration 1 upon r dr. Both are same. Whether I write r raised to minus 1 or whether I write it as 1 upon r. What is my power? What should I remember? Write the variable. Variable is r. Then power plus 1 upon power plus 1. So what is my answer here in this case? R raised to 0 upon 0. Okay, so this is answer is 0 itself. Fine. It is r raised to 0 upon 0. So anything raised, or you can even say it as undefined. Fine. Okay. Now next, because it is divided by 0, undefined. Let us take r raised to negative 2 dr. What is my integration here? 1 upon r square dr. Okay. So whether this or this both are same. Now what is my way of doing, or what is my trick of doing? Write the variable. Write the power plus 1 upon power plus 1. So what is my answer? R raised to negative 1 by negative 1. Now like this I cannot put it. So I have to put it in proper format. Here I have written r raised to minus 1 as 1 upon r. So let me write it as 1 upon r. And negative here is there, so I write it as negative. Clear? So whether I have a positive power or a negative power, my trick is write the variable, write the power plus 1, divide power plus 1. And then finally I have to put it in a proper format. Also one more negative example we should do. R raised to minus 3 dr. Okay. So what should I do? R raised to negative 3 plus 1 upon negative 3 plus 1. What is negative 3 plus 1? Negative 2 upon negative 2. Now I have to write it in a proper format just like this. So r raised to minus 2 can be written as 1 upon r square. Negative, I'll take it. And 2, I'll write it here. So what is my answer? Negative 1 upon 2r square. Clear? So, this is the formula of the integration we are going to do just now in our derivation. Now, other than this, once the integration is over, I can even apply the limits. Now, what are the limits? What is the meaning of the limits? Suppose this limit is, I write it as 0 to 2. That means I am summing up. What is the meaning of this? I am summing up from 0 to 2. Correct? I don't want the other values. I only want to sum up the part from 0 to 2 scale. So what I should do here? I have to finish my integration. I have finished my integration, and then I have to apply the limits 0 to 2. So what is the meaning, or how should I apply this limits 0 to 2? Instead of the variable, I write this upper limit 2 square upon 2 as it is, minus lower limit 0 square upon 2. So what is my answer here? 4 upon 2, or simply I can cancel this because it is divided here. So 2 and this is 0. So my answer is 2. Agree? So what are the two steps? First integration part and then applying the limits part. How should I apply this? One example only I have given you. How should I apply the limit? Upper limit minus lower limit. What should I do in applying the upper limit? Just put the upper limit in the place of variable. I have put 2 in the place of r. Solved it. Minus 0 in the place of r. Solved it. Whatever answer I get, that is the limit I have applied from 0 to 2. Correct? So, remember this as a curriculum itself from now onwards in physics of class 12. Whenever there is an integration, use the formula variable raised to power plus 1 divided by power plus 1. Then if limit has to be applied, upper limit minus lower limit. What is the meaning of applying the limit? Just substitute the number in the variable place and solve. We will use it just now so that you will also be very clear with what I am trying to do. Now, take a pic of what we have done just now so that All these examples you can revise and understand in your way. Self-study is the best study. I'm just moving. You take a pic. Then we will go back to the derivation. Okay. So now we go back to the derivation of potential due to a point charge. Okay. Now, where is our point charge plus Q? So, it is very important for you to draw the diagram by yourself. So, you must understand the diagram and you must understand every variable in the diagram. So, let us go one by one how you should draw it. Correct? Okay. Now, here we have Q is a point charge whose potential we want to find out. Okay. Now, where is it kept? At the origin. O is the origin. So, we have a point charge capital Q kept at the origin. Okay. What is the point P? P is the point where we want to find the potential. What is its position vector? R. What is it? Position vector from O, the origin. So, R is a position vector of the point P from the origin. That is R. Slowly we will define all the terms which I have written. Okay. Now, we want to bring this positive charge of 1 coulomb from infinity to the point P. This is the point P. Now, on its way from infinity to the point P, let us consider one point P dash. So, the charge 1Q, 1C is coming from infinity to P. On the way, we are considering a point P dash, where we can write down the force of repulsion between this positive charge and this positive charge. Both are positive, so they will repel. What is that force of repulsion between the charge Q and 1C? So, what is the force? Fe is equal to, what is the formula? K. Q1, Q2 upon R square. Correct? Here, we can write K. What is our Q1? Capital Q. What is our Q2? 1. What is the distance between Q and P dash? At present, our charge is at P dash. So, what is the distance? R dash square. If I have written it as a vector, so here also I will write it as R dash cap. Okay. So, force Fe is the electrostatic force of repulsion between capital Q and 1 coulomb. The distance between these two charges, as can be seen, is R dash. That's why I have written R dash square, R dash cap. Clear? This is the force of repulsion between Q and plus 1 coulomb. So, what is R dash? R dash is distance between, I will write in short for increasing the speed, between Q and P dash at present. Okay, fine, it is there. Now, on the way, we have stopped at P dash and we have calculated the force which is existing. Okay, Now further, let me move this charge 1 coulomb by a distance of delta r dash. Okay, so delta r dash is one small distance I am moving against this repulsive force. Correct? So the direction of displacement delta r dash is towards Q, but Q is pushing this charge 1 coulomb against it because it is repulsion. So the force of repulsion on 1 coulomb is in this direction, opposite direction. So here the direction between the force and displacement is opposite. So what is the angle between these two? 180 degree. And what are we trying to find out? The work done in this process of bringing that charge. So what is the work done? Delta W is equal to this force. Okay, how much? K, Q into 1 is Q, R1 square delta R dash. Agreed? And it is a dot product between the force and the displacement delta R dash. So if it is a dot product, then what is the angle between them? These two? Between the force and the displacement? 180 degrees. So cos 180 degrees. So if cos 180 degree is equal to -1. That I write here. Dot product is having an angle between them 180 degrees, which is equal to -1. I am writing here. So what is my answer here? Delta W is a scalar. Okay. This is a dot product. So K, Q upon R dash square delta R dash. Correct? Why I have written negative here? Because the angle between them is 180 degree. Okay, so I have written negative here. And very important here, we have to remember, when Q is greater than 0, delta W is also greater than 0. Okay, that also we have to remember. That's why this negative symbol is written, because our displacement is in opposite direction for this work done. That way also you can put it. Now comes our work of maths. Okay, what is our work of maths? Integration to understand the total work done. So to get the total work done, I must integrate on both the sides. What is the limit? From where to where I am bringing this charge? From infinity to the point P. And where is the point P? At the position vector R. So what is my limit here? Infinity to R. Infinity to R. Just now I told you about upper limit and lower limit. Starting point is lower limit, ending point is upper limit. Here also I can write infinity to R. Here this is the meaning, total work done. And here, whenever there is integration, whatever constants are there, I have to bring them outside. What are the constants here? Negative, K, Q. These are the constants. Now, whenever there is integration, delta R will become dr. Okay, upon R dash square. So what have I converted? This delta R is little big value. Yesterday I told you dr is a very small value. Integration is always for small values. So I have converted delta R to dr. Now I am ready with the integration and the upper limit and the lower limit, which I have just now taught to you. What is the variable here? R dash. You have to search the variable. So if the variable is R dash, then what do I write? Negative KQ integration infinity to R. Okay. R dash raised to minus 2. I'm bringing it up. D R dash. This is my integration ready. Fine. Okay. Now only I have to integrate it. My work will be done. Fine. Okay. So we have got in this equation small work delta W to move the small distance displacement delta R. So for the complete work, we integrated both the sides from infinity to R. So W is the complete work which is given as negative KQ integration R dash negative square. Now we have to do the integration of this part, which we have learned just now. What was the trick I gave you? Write negative KQ outside and use our trick. Then apply the limit. So we are going to use the trick. What is the trick? The trick is write the variable. Because it dash is there, I'll put a bracket here. Write the power plus 1 divided by power plus 1. Integration is over. Then apply the limit. What is the limit? Infinity to R. Simple. Okay. So write the variable power plus 1 upon power plus 1. So what is this? We can write it as negative KQ R dash raised to negative 1 upon negative 1. This negative and this negative becomes plus. I am only left out with R dash raised to negative 1. Now, what is my limit? Limit is infinity to R. So I have to apply the limit now. Okay. So how do I apply the limit? Upper limit minus lower limit. Okay. Is equal to KQ. Now I have to apply only the limit. So upon 1 upon R dash raised to minus 1, I brought it down. So 1 upon R dash, nothing is there, down 1 is there. Okay. So infinity is the lower limit, R is the upper limit. So I apply those limits. I get W is equal to KQ. Applying upper limit to R dash, that means instead of R dash, I substitute R. So 1 upon R minus lower limit, instead of R dash, I substitute infinity. What is 1 upon infinity? 0. So what is my final answer? W What is my final answer? I write it here instead of making it clumsy here. W is equal to KQ upon R. Okay, where is 1 upon infinity? 0. And KQ was outside 1 upon R, so I wrote it below the KQ. So my final answer is work done is equal to KQ upon R. Right? Now for what I have done this work? I have done this work to bring a unit positive charge from infinity to R. That's why my lower limit and upper limit are R and infinity. Correct? So that work done is the potential energy itself, which is a function of the distance between the charge and the point where I want to find out potential. Correct? So V, R, what is V? Potential. As a function of R is equal to KQ upon R. This is the work done which is the potential to bring a unit positive charge from infinity to R, which is the potential which we are trying to find out for a point charge Q at a point P. Clear? Now, quick revision. What is the force between these two charges? Written here. What is the small distance we are bringing? Delta R. What is the angle between the force and delta R? 180 degree. So the work done is a dot product of force and displacement. I wrote here. Correct? And written a negative symbol because delta R is opposite to the force. Integrated from infinity to R such that I get the total work is equal to KQ upon R. That work done itself is the potential energy of the charge at a point P from the charge. Okay? Clear? I hope I am clear with what I am doing. Now, in the very next page of this same video, keep listening. I will do a graph of V versus R because K and Q are constant. That graph is asked. This also is the derivation is asked. I'll just move you, take a pic. Okay? Now, as asked in the board exam or the entrance exam, there can be a common graph of E or V on the y-axis and R on the x-axis. First, let us write out the formula of E. E is equal to K Q upon R square. Therefore, E is inversely proportional to R square. Similarly, just now we found out V is equal to K cube upon R. Therefore, V is inversely proportional to R. Okay, so using these proportionalities, we plot a graph for both these values on the same coordinates. Okay, so first let us draw for E, that is, it is a negative graph as seen. Okay, and then let us draw for V. Both are inversely proportional to R. Okay, so I write down this is the graph for E versus R, and this is the graph of V versus R. Now the question here can also be asked, can there be a point of intersection having same value of E and V? Yes. Here E is equal to V. Okay, that's why there is a point of intersection between these graphs. Fine, the value of E and V are same at this particular point. Fine, okay, so this kind of graph can be asked either combined for E and V or separately for E and V. Okay, so learning the formula, immediately you should be even able to plot the graph. Fine, okay. Now, when can I have Vmax for the same setting? R should be very close, near. Okay, R should be very near to the point Q or to the charge Q. And when can I have V 0? V is equal to 0 for R is equal to infinity. What does this mean? That when R is equal to infinity, the potential is 0. Why? So what answer we will get? V is equal to K Q upon R is equal to infinity. So I substitute infinity here. So anything divided, any number divided by infinity is 0. What does it mean? That for a point at infinity, the potential is 0. Remember that. Okay? Clear? Follow? Okay. So I shall just move. You take a pic of whatever I have done just now, photograph and the remembrance, and keep it in your mind. All the small points will be asked as multiple choice questions or 1 markers or assertion reasoning. Remember these points. Okay?